There will be two types of analyte that present in the dark chocolate, which is organic analytes and also for inorganic analytes. For organic analytes, there will be fats, which is the cocoa butter, sugars, and also bioactive components. Whereas in inorganic analytes, there will be minerals such as magnesium, trace elements such as iron and also copper, moisture, and also for heavy metals such as lead, cadmium, and also arsenic. So these are the analytes that we chose for this analysis, which is lead, cadmium, and also arsenic. For the sample preparation, we use microwave digestion. And then for the preparation of the solid dark chocolate sample, we chill the dark chocolate until hard and then grate it using the blender with fine granular condition, mix it, and then preserve in a tightly stopped bottle and store it in cool plates. For the reagents, we need to prepare concentrated nitric acid, but we dilute it into two different types of concentrations, which is 0.1 N and also 3 N. And then after that, we also need to prepare hydrogen peroxide as well. First, we weigh 0.2 to 0.5 dry dark chocolate powder sample into the vessel and then follow up with 5 ml of 0.1 N nitric acid and also 2 ml of hydrogen peroxide into the vessel. And then for this analysis, there will be 16 vessels involved for one time. So hence, we need to prepare 15 vessels with the chocolate sample and then another one is the reagent blank. And then after prepare all 16 vessels, we close up the vessels and then place it inside the vessel holder and then place the holder inside the microwave oven and then set the oven program according to the parameters below. After the digestion was complete, we need to remove all of the vessels and let them cool thoroughly and then open and rinse down the lid and also the walls into the container. Transfer the solution into a 25 ml volumetric flask and then dilute to mud with the deionized water. If the solution needs more dilution due to the high metal concentration inside, we need to dilute the solution with the 3M nitric acid to maintain the same acid concentration. And then finally, we transfer the solution into a plastic container for the sample storage.
The picture below is the instrumental analysis technique of graphite furnace AAS. Right now, I will talk about how GFAS works. The first one is sample injection, second one is heating and atomization, and the third one is light absorption. In GFAS, a known amount of sample solution is injected into a graphite tube, which can be heated to vaporize and atomize the analyte. The atoms absorb ultraviolet or visible light of an element-specific wavelength and make transition to higher electronic energy levels. Then, the fourth one is atomic absorptions, fifth is measurement of absorptions, sixth is calibration with standards, and the seventh is quantifications. The amount of absorption is a measure for the concentration of the element of interest in the sample solutions. Concentration can be derived after calibrating the instruments with standards of non-concentrations. GFAS is recognized for its good sensitivity, allowing the detection of trace amount of element with high precision. The techniques achieve low detection limits, making it suitable for the analysis of samples with low concentration. It is versatile and can be applied to diverse sample matrices, including liquids and solid. It requires relatively small sample volumes, which is advantageous when dealing with the limited samples. It is accurate and reliable as it is less susceptible to spectral interference compared to other techniques. One drawback of GFAS is that the analysis process can be time-consuming. It is generally limited to the sequential analysis of a small number of elements in a single run. The technique may have the limited dynamic range for sample with a wide concentration range of target elements. It lacks the ability to screen the multiple elements simultaneously as it is designed for the accurate determination of specific elements. Optimization of the GFAS method is necessary for different sample types, adding an additional step to the analytical process.
Now we will have a look on the GFAS instrumentation. Firstly, the hollow cathode lamp emits the light and the background absorbent is removed before entering the graphite furnace. Next, the sample is introduced through the hole on graphite furnace while the inner gas is flown to avoid any oxidation but stop during the atomization stage. The light continues to pass through the monochromator, detector, and finally come out as a radar. First, hollow cathode lamp. It is made from tungsten anode and cathode is composed of the element being analyzed later. When a large voltage passes across anode and cathode, the inner argon gas will ionize and then accelerate to the cathode, sputtering off and vaporize atoms from the cathode. The vaporized atoms will be excited by collisions with inner gas ions and finally emits light. Next, graphite furnace aka electrothermal atomizer is the place where atomization occurs. First, a few microliters of sample are deposited onto the leaf platform to enhance the atomization efficiency. Then, a programmed series of heating events, which is drying, pyrolysis, and atomization, are carried out at specific time frame and temperatures. Now, we will have a look on the monochromator. From the diagram above, we can see that these are the components of monochromator. And then from the video below, we can see that how the monochromator selects the specific wavelength of light by adjusting the dispersing device. The detector that we use in GFAS is PMT, photomultiplier tube. First, the photon strike the cathode and the electrons are emitted. Next, the electrons are accelerated towards a series of diodes by increasing voltages, and additional electrons are generated at each diode. Finally, the amplified signal is collected and measured at the anode.
The protocols for chocolate analysis consist of 5 stages, which are calibration, instrument operation, data analysis, quality control, and reporting. The method used in calibration stage is standard additions calibration method. First, 10 ml of aliquots of sample solution are prepared. Then different amounts of analyte standard solution are added to each aliquot. The concentration added must be in expected concentration range of the sample. Last, each aliquot is diluted to 50 ml with acetic acid and mixed well. The standard method used is AOAC official method 999.10, where the sample and standard solutions are mixed to make a standard addition curve, and the curve must consist at least 3 points. The requirements of the highest and lowest standard also need to be followed. Chocolate is a complex matrix sample. The components like fat and sugar will affect the accuracy in determination of the analytes. Thus, standard addition calibration method is useful in this case as it allows the quantification in unknown matrix. The matrix effects are minimized by adding the analyte to the sample. The standard addition method can be used when the matrix effects appear or matrix match sample are not available, but it is quite time-consuming to perform a full calibration for one sample. The problems such as baseline shift or slope of line not accurate may also occur. There are limitations when using this method, such as it must be free of spectral interference. All measurements of analytes can be carried out using graphite furnace instrument with a deuterium spectral collection lamp and pyrolytic graphite tubes. The operating parameters of the instrument need to be adjusted as shown in the table below to have the highest sensitivity.
Next, I will proceed with the sample analysis and data analysis. First, we need to measure the adsorbance of each sample solution by introducing the sample into pyrolytic graphite tube of a graphite furnace atomic adsorption spectrometry instrument. Then we plot a calibration curve of adsorbance versus concentration of either analyte. Then we can obtain the original concentration of the lead, cadmium, and the arsenic in the chocolate sample by calculating the S-intercept of a curve and multiply by -1. Then we multiply the concentration of the analyte by the dilution factor. For the calibration graph, the measurement must be within the linear range because accurate relation cannot be obtained from the non-linear calibration point. To have a better the correlation between Y and S, correlation coefficient of a calibration curve must be greater than the 0.999 as an evidence of acceptable fit of a data to a relation line. Next is a quality control. The quality control measure can be run by analyzing a band solution and the quality control sample with a known concentration of the analyte, lead, cadmium, and arsenic. Besides that, the recovery relative standard deviation and the confidence interval of a result should be calculated and compared with the acceptance criteria to ensure the reliability and the accuracy of a result. According to a standard method APH A3125B, the recovery of a spice sample should be within 80 to 120%. The relative standard deviation of a quality control sample should be less than 10%. Lastly is a reporting. In a report, we need to provide the detail of a sample preparation, instrument operation, calibration procedure, data analysis, and the quality control measure. We also need to expect the concentration of analyte, lead, cadmium, and arsenic in the chocolate sample, including detection limits and relevant statistical data. Then we compare the result with the relevant standard to ensure the chocolate sample is set to consume. This slide shows the relevant standards of chocolate set by the College Alimentarius Commission, World Health Organization, and the European Union.